During the mid-1960s, a pioneering group of Lockheed engineers set out to develop a revolutionary new weapon system for the US Army. The result was the AH-56 Cheyenne, an aircraft that combined the flexibility and maneuverability of a conventional helicopter with the speed and stability of a fixed-wing aircraft. The Cheyenne was one of the first aircraft to successfully harness the phenomenal control power of a rigid rotor, enabling pilots to easily conduct high-speed maneuvers during nap-of-the-earth flight. The system was compounded with a pair of stub wings and a powerful push-up prop that provided rapid acceleration to speeds in excess of 230 miles per hour. On board, an advanced, fully automated fire control system allowed the Cheyenne's two-man crew to simultaneously launch devastating attacks in every direction. Massive barrages of 30mm cannon fire, 40mm grenades, and even 2.75-inch rockets could all be delivered with pinpoint accuracy. The Cheyenne's fully integrated weapon system also featured extremely advanced range-finding and navigational aids that made it perfectly suited for a more hazardous mission: tank busting. With the push of a button, the gunner could lock a tank's coordinates into the fire control system. The pilot was then free to maneuver in and out of rolling terrain or to use the pusher prop to rapidly decelerate into a concealed firing position. At any time, the target could be reacquired almost instantly and destroyed with one of up to 36 TOW anti-tank missiles. By early 1969, extensive tests were being conducted on 10 Cheyenne prototypes. Onlookers were regularly astounded by the aircraft's phenomenal capabilities. Many of its new subsystems had been designed from scratch and would come to revolutionize aircraft and weapons development for decades. The Army was so pleased with the system that it authorized production of 375 Cheyennes under a contract that ultimately would have delivered more than 3,300 aircraft. Incredibly, though, not a single production model would ever be built. This is the amazing story of the rise and the fall of the Lockheed Cheyenne. The strange saga of the Cheyenne began in the late 1950s with a simple radio-controlled model. Lockheed engineers had been searching for a way to develop a small helicopter for everyday use that was easy to fly. They designed the model to see if it was possible to rigidly attach rotor blades directly to a helicopter's hub, rather than to the lead lag and flapping hinges used on most conventional systems. By doing so, they theorized that the inherent instability of all helicopters could virtually be eliminated. The engineers were right. And within a few months, a scaled-up version of the model, known as the CL-475, had been built to conduct additional tests. Helicopter designers had been forced to settle on unstable, hinged rotor systems in order to overcome gyroscopic forces produced by spinning blades. Lockheed's rigid rotor concept incorporated a separate control gyro designed to help offset those forces. The blades were linked to the gyro by individual control arms. The gyro, like any rapidly spinning object, wanted to remain in a fixed plane of orbit. As a result, it naturally forced the control arms to adjust the pitch of the blades as necessary, ensuring that the entire helicopter would remain on the same plane unless otherwise directed. This surprisingly simple system proved to be extremely stable in flight, yielded a phenomenal amount of control power and was extraordinarily easy to operate. In fact, the Model 475 was so easy to control that a mechanic who had flown in small aircraft once flew it back from the desert rather than tow it in, even though he had never flown in a helicopter. To dramatically illustrate just how stable the new platform was, Lockheed engineers perched a man on a boom attached to the side of the aircraft. The man's weight created an enormous offset to the center of gravity that would have been extremely difficult for conventional rotor systems to handle. But the 475 automatically compensated for the offset, easily maintaining level flight. The success of the 475 led Lockheed to enter the US Army's 1961 competition for a new light observation helicopter. 3 more conventional designs were selected, but the Army was impressed enough with the Lockheed's rotor system to award a separate contract. The result was the AH-56, a somewhat bigger and more refined helicopter designed and built solely to test the capabilities of Lockheed's rigid rotor. The 51 quickly demonstrated a degree of stability never before achieved in a helicopter. For the first time, handling qualities were equivalent to those of a fixed-wing aircraft. Expanded stability tests indicated that the new system produced an even larger center of gravity than in the 475. In this phenomenal sequence, a man perched on a 16-foot boom effectively moved the helicopter's CFG more than 10 inches without upsetting the rotor's natural ability to maintain a hover. Other demonstrations indicated that the system could also easily handle rapid shifts in the center of gravity. These unusual properties would eventually allow Lockheed engineers to push the envelope of helicopter performance to extraordinary heights. Unlike the Model 475, the AH-51 reflected jet-age technology. It had a streamlined fuselage with flush riveting, retractable landing gear, and control rods that were located inside the rotor shaft. Throughout early 1963, extensive test flights were conducted on 2 AH-51 prototypes by Lockheed and by the pilots of a joint Army-Navy evaluation program. The unique rigid rotor configuration continued to exhibit numerous advantages over conventional rotor systems, including the ability to maintain phenomenal pitch and roll control even at zero gravity. But one factor in particular emerged to become a driving force in Lockheed's helicopter development program: speed. Within 4 months of taking flight, the AH-51 had been flown at 160 miles an hour. Eventually, it would reach speeds in excess of 200 miles an hour, an incredible feat even by today's standards. The AH-51's capabilities proved to be so phenomenal that they attracted interest from the National Aeronautics and Space Administration. Eventually, NASA officials even ordered a 51 of their own to conduct additional research on the flight characteristics of hingeless rotor systems. The tremendous success of the program convinced Lockheed officials that there were strong possibilities for a commercial venture. As a result, the company built 2 modified versions of the 51 for themselves under the designation Model 286. The 286 was a 5-seat utility helicopter expressly designed to increase public interest in the benefits of the rigid rotor system. Like its predecessor, it was fast, stable, and extremely simple to fly. The cockpit even featured trim systems just like those found in fixed-wing aircraft to help pilots set and maintain specific aircraft attitudes while in flight. To clearly illustrate the incredible control power of the 286's rigid rotor system, Lockheed pilots conducted several spectacular airshow demonstrations. The pilots performed numerous rolls, loops, split S's, and other thrilling aerobatic maneuvers that were virtually impossible to duplicate in conventional systems. The agility and maneuverability of the unusual helicopter regularly astounded spectators. But it was the pilot's ability to maintain positive control power, even during inverted flight, that shocked aviation experts from around the world. Lockheed successfully carried the 286 through FAA certification in 1966. Unfortunately, a lack of commercial interest coincided with several major setbacks on other Lockheed contracts to prevent the helicopter from ever reaching production. But the rigid rotor revolution that Lockheed engineers had started was far from over. In 1963, Lockheed engineers began developing a compound helicopter under a broader US Army effort to further explore the possibilities of high-speed flight. Their goal was to build on the earlier successes of the AH-51 by adding a pair of stub wings and a jet engine to the fuselage. After conducting preliminary wind tunnel tests on a scaled model, the team began modifying one of the existing airframes to withstand the unusual configuration. Among other things, additional reinforcement had to be installed around the plexiglass windshield in anticipation of the higher speeds expected in compound flight. The compounded AH-51 was then subjected to extensive structural testing to ensure that the airframe could handle the generated by the newly integrated wing and engine. The jet engine selected for the compound system was a Pratt & Whitney J60 that could produce up to 2,600 pounds of thrust. The weight of the engine was offset by a pod mounted on the right wingtip that contained flight test equipment and a battery. The rigid rotor assembly was identical to the system that Lockheed's pilots had flown on pure versions of the AH-51. Don Segner, one of Lockheed's engineering test pilots, became the first man to fly the bizarre-looking configuration. He was also the first to fly the 51 and the 286, and had conducted exhaustive flight testing in both models. The first flights of the compound revealed that the structural loads and stable handling qualities were basically the same as those achieved in the pure helicopter. In fact, the rigid rotor system remained incredibly nimble despite the additional weight and drag of the engine and stub wings. The basic goal of the compound system was to eliminate a phenomenon known as retreating blade stall. As the forward speed of a helicopter increases, the relative pace of the blades on the lagging or retreating side of the rotor disc begins to diminish rapidly. At extremely high speeds, the relative pace of the retreating blades is reduced so much that they are no longer able to create sufficient lift on that side of the helicopter. The compound system was designed with stub wings and an engine, so that the rotor could be relieved of most of its lifting and propulsive duties during high-speed flight. As the pilot increased forward speed, he could simply reduce the collective pitch of the blades and allow the wings to take over. Control power was still derived from the cyclic pitch of the blades, as opposed to the conventional control surfaces found on most aircraft wings. But it rapidly became apparent that at higher speeds, the compound system performed just like any other fixed-wing aircraft. As the flight envelope of the compound was gradually expanded, many unique capabilities emerged. Thrust from the jet engine allowed pilots to rapidly transition to forward flight and to climb out at an astonishing rate of more than 3,500 feet per minute. But the primary goal of the Army's compound helicopter program was speed. As a result, Lockheed's test pilots embarked on a program to push the system to its limits. Hundreds of flights were conducted in an effort to gradually expand the flight envelope. By May of 1965, the compound had been driven to speeds in excess of 270 miles per hour. Engineers were forced to make several modifications as speeds increased. Additional bracing had to be added to the forward windscreen after the plexiglass began to bend in on a pilot during one high-speed run. But flight tests continued. Eventually, the system set an unofficial speed record of 303 miles per hour. In 1967, Lockheed embarked on another test program to see just how fast and low the compound could be flown and how susceptible it would be in combat. To avoid detection, pilots often maintained speeds of more than 250 miles an hour at altitudes of less than 30 feet. Observer teams were stationed along a predetermined route to simulate typical weapon emplacements and record aircraft detection times. The results were phenomenal. Aircraft tracking proved to be extremely difficult for the observers, and even for the experienced cameramen set along to document the event. The AH-51 compound was ultimately impractical for any other use but research. But the entire program delivered a clear message to the US Army. The extreme speed and maneuverability of compound systems in low-level flight could dramatically increase both the potency and survivability of helicopter pilots in combat. As a result, Army officials gained enough confidence in the compound concept to include it in plans for an entirely new generation of aircraft. The US Army had been exploring the feasibility of arming helicopters since the mid-1950s. Initial configurations were relatively crude, but by mid-1957, a small group of pioneering aviators had successfully armed several helicopters and were regularly conducting dramatic demonstrations of aerial firepower. By the time the US had become embroiled in the Vietnam War, the concept of armed helicopters had become an essential element of Army combat operations. Helicopters became the principal means of moving men and supplies in and out of combat throughout Southeast Asia. But they proved to be extremely vulnerable to ground fire. As a result, hundreds of Bell UH-1 Hueys were modified to carry a potent arsenal of machine guns, grenade launchers, and rockets. These gunships were used to escort troop transports throughout the country, to clear landing zones of enemy opposition, and to provide close air support once men had been inserted on the ground. There was one major problem, however. The Huey had not been designed to handle the weight of guns, rockets, and ammunition. Thus, many of the gunships had considerable difficulty maneuvering around and even keeping up with the troop carriers they were assigned to protect. In 1964, engineers back at Lockheed's California company developed a proposal that they believed could remedy the situation for years to come. The proposal was developed in response to an Army competition launched that same year for an advanced aerial fire support system. 11 other companies submitted design concepts under the competition. But in the end, Lockheed was awarded a contract to build and test 10 developmental prototypes. The new aircraft would be known as the AH-56 Cheyenne. The requirements for the Army's advanced aerial fire support system were extremely ambitious. Among other things, the aircraft had to have a dash speed of more than 250 miles per hour, which at the time had only been achieved by jet-assisted compounds. It also had to have a ferry range of more than 2,400 miles, the distance from California to Hawaii, and the ability to hover out of ground effect at 6,000 feet, a huge challenge. The extreme requirements forced Lockheed engineers to create many new systems and fabrication techniques from scratch, and to develop a vast array of unconventional methods for testing new components. One of the most unusual was a massive whirl tower constructed in the natural bowl of a nearby canyon. The tower was designed to thoroughly test the structural integrity and hover performance of the enlarged rotor system before it was installed on any of the 10 prototypes. On April the 16th, 1967, the first AH-56 was rolled out of a California hangar where most of the production took place. The new model was given the name Cheyenne, in keeping with an Army tradition of naming aircraft after Native American tribes. The Cheyenne's compound system featured a pusher prop instead of a fuel-hungry jet that was linked to the same drivetrain as both the main and tail rotors. The control gyro and rigid rotor system was extremely similar to the one employed on the XH-51, but had been scaled up to suit an aircraft that was more than 4 times its size. To ensure that the extension had been successful, the first model was moved into a large circular stockade that became known as Fort Cheyenne. Here, the prototype ran day and night for hundreds of hours in tie-down test to check out the performance of the drive and rotor systems. The stockade had 2 heavy plank walls with more than 8 feet of gravel between them, just in case anything went wrong. On September 21st, 1967, the Cheyenne took to the air for the first time. At the controls that day was Don Segner, the engineering test pilot who had also conducted first flights in both models of the XH-51 and the 286. Initial flight testing went surprisingly well, considering the complexity of the aircraft and the speed at which it was developed. The system quickly demonstrated most of the same positive handling characteristics as previous rigid rotor systems, and even surpassed some of the capabilities of the jet-assisted compound. The pitch of the pusher prop could actually be reversed for rearward flight. But the propeller system could still generate enough thrust to allow for rapid transitions into forward flight and climb out without nosing over, just like the compounded AH-51. Over the course of several months, hundreds of flight tests and military demonstrations were conducted in an attempt to gradually expand the Cheyenne's flight envelope. Like earlier compounds, the AH-56 could basically be described as an aircraft with an extremely effective lifting device. At higher speeds, support from the stub wings allowed the pilot to virtually excuse the main rotor from its lifting role so that he could attain much higher speeds. Within a few months, Lockheed's pilots had pushed the Cheyenne to speeds in excess of 230 miles per hour. The pusher prop emerged as one of the Cheyenne's greatest assets. Since blade pitch could be reversed, it could be used not only to propel the aircraft to high speed, but to slow it down as well. This same capability also allowed the pilot to actually put energy back into the main rotor system if the engine happened to cut out while in forward flight. He could then auto-rotate to the ground or even climb to a safer auto-rotation altitude with little difficulty at all. Several technical problems did emerge during flight testing, however, such as a lack of stability both at low altitudes and high speeds. But most of these initial problems were systematically addressed and ultimately resolved. As the flight program continued, Lockheed engineers conducted extensive testing on the Cheyenne's potent arsenal of weapons. The program represented the first time in history that a helicopter had been developed with a fully integrated weapons system. Dozens of new subsystems had to be developed to monitor, aim, feed, and fire the weapons, which included a 40mm grenade launcher, a 30mm cannon, a minigun, rockets, and eventually even wire-guided tow anti-tank missiles. After conducting extensive ground tests to measure the effects of weapons firing, a fully integrated model was prepared for in-flight firing. The Cheyenne's weapon system was extraordinarily sophisticated for the time. The platform could carry up to 8,000 pounds of ordnance, which typically included 2,000 rounds for the 30mm gun, 780 rounds for the 40mm grenade launcher, up to 114 2.75-inch rockets, and 6 tow missiles. The guns and the tow missiles were controlled by a co-pilot gunner who sat in a turret that could swivel through 360 degrees. The gunner's turret incorporated a stabilized lower sight head that contained a tracker for tow missiles, a 12-power optical sight, a laser rangefinder, and an infrared night vision sight. An early helmet sighting system also allowed the pilot to control the guns by simply moving his head with the target. The fire control system was fully automated. All the gunner had to do was place the reticle of his optical sight on the target and activate the laser rangefinder. From that moment on, the sight remained locked on to the target, regardless of aircraft maneuvers. A central computer combined sightline and range information from the swiveling gunner's station with speed and attitude data from 2 inertial gyros and a Doppler radar system. The computer then calculated all weapons corrections and aimed the guns for maximum accuracy, taking into consideration winds at altitude and the ballistics of the weapons selected. An on-board auxiliary power unit allowed the aircraft to stand by indefinitely with all systems up, so the crew could scramble at a moment's notice from even the most austere sites. The Cheyenne was designed to serve in remote locations without ground support equipment, so that it could respond immediately to the often desperate needs of commanders in the field. An advanced navigation system allowed the pilot to rapidly reach new destinations with great ease. The coordinates of multiple targets could be entered into the self-contained system at any time. The pilot was then able to quickly reference the real-time range and bearing of any of the targets with the push of a button. In August of 1968, Lockheed pilots conducted the first of many in-flight firing tests. Initial runs were made with a 7.62mm minigun to measure the accuracy of the automated fire control system. The crews repeatedly struck multiple targets with incredible precision, even at a distance of more than 750 meters with offset angles of up to 70 degrees. Other weapons, such as the 40mm grenade launcher, were soon installed and tested extensively with the same phenomenal results. Officials, both at Lockheed and in the Army, were extremely impressed by early in-flight demonstrations. The Army became so confident in the system's overall potential that it authorized production of 375 Cheyennes under a total procurement package that ultimately would have generated more than 3,300 aircraft. But a major problem soon arose during efforts to expand the Cheyenne's flight envelope even further. On March the 12th, 1969, tragedy struck when one of the 10 prototypes went down off the coast of California, killing the pilot. The accident occurred during a flight to investigate a variation in rotor thrust that sometimes occurred at high speeds. The phenomenon, known as the half-P hop, caused the pilot's arm to operate the collective lever to an ever-increasing amplitude. The uncontrollable action, commonly known as pilot-induced oscillation, continued until the rotor blades came crashing down through the Cheyenne's tail boom and canopy roof. Significant problems and even major accidents are often encountered during the development of a new aircraft, especially with an aircraft as revolutionary as the Cheyenne. But this crash triggered a response that marked the beginning of the end, not only for the Cheyenne program, but for Lockheed's entire rotary wing effort. Within a month, Lockheed officials received a cure notice from the Department of Defense requiring them to fix a variety of existing and even anticipated problems with the aircraft. The company was given 15 days to prepare a response, which they did in a frantic attempt to save the program. But the answering document was not enough. Less than 3 months after the accident and only 6 months before the first aircraft was to be delivered, the production contract for the Lockheed Cheyenne was officially cancelled. While the production phase of the Cheyenne program had been terminated, development efforts continued under an Army contract of reduced scope. A blue ribbon panel of government and industry specialists was appointed to monitor the remaining program. And in July of 1969, flight trials were resumed to test several modifications. Many observers claimed that the tragic accident had been caused by the Cheyenne's rigid rotor, which they maintained was inherently unstable. But subsequent testing revealed that it was the control system and gyro stabilizer, not the rotor, that caused the half-P hop at high speeds. As a result, the gyro was eventually moved from the top of the rotor to below the transmission. It was also made smaller, lighter, and faster turning, and was provided with a feedback path to detect blade root bending. This advanced mechanical control system was put through an extensive flight test program, both by Lockheed and the Army. A separate electronic control system was also designed, just in case the mechanical modifications failed to correct the problem. By the end of 1970, flight tests had been completed to everyone's satisfaction. The Cheyenne performed incredibly throughout the tests. High-speed maneuvers had included pull-ups to 2.6 Gs and push-overs to minus 0.2 Gs. Absolutely phenomenal for a helicopter. The system had also reached a top speed of nearly 250 miles per hour in level flight and more than 277 in a dive. Extensive in-flight firing tests were also conducted at the Army's Yuma Proving Grounds in Arizona to evaluate the full potential of the Cheyenne's weapon systems. The level of accuracy proved to be absolutely phenomenal. The first shot from the 30mm cannon consistently hit a 10-inch bullseye at a range of 2 miles. A typical demonstration featured the crew's ability to strike multiple targets during a single firing run. Here, the gunner strikes a primary target with 30mm rounds, while the pilot provides suppressive fire with the 40mm grenade launcher. Even as the pilot's rounds continue to hit with devastating precision, the gunner was able to launch a third strike against a mock convoy with a massive barrage of rockets. Other demonstrations featured the potency of the TOW anti-tank missile when used in conjunction with the combined automatic navigation and fire control system. In this sequence, the gunner acquires a tank a few miles out. With a push of a button, the tank's coordinates are locked into the system, allowing the pilot to freely maneuver into a better firing position several miles up a narrow valley. With earlier dynamic problems apparently resolved, and all other systems working extremely well, Lockheed officials hoped that the production contract for the Cheyenne would be reinstated. But it would not prove to be that easy. Several unrelated issues had been gaining momentum and would ultimately coincide to bring an end to the program. First, a debate apparently emerged over the difference between the roles and missions of the Army and those of the US Air Force. Opponents of the Cheyenne argued that one of the helicopter's primary missions, close air support for ground troops, was a responsibility that had traditionally been assigned to the Air Force. In fact, the Air Force had initiated a design competition of its own for a new close support aircraft at about the same time that the first Cheyenne rolled off the assembly line. A prototype of the new aircraft was expected to fly in early 1972, and procurement plans for more than 700 production models were in the works. Many who participated in the Cheyenne's development believe that its high-speed ground attack capabilities threatened the very existence of the Air Force's program, thus creating considerable opposition to the project from the very beginning. As the roles and missions dispute evolved, another situation arose that would have a tremendous impact on the fate of the Cheyenne. In 1969, Bell Helicopter convinced the Army to buy 1,000 models of a new attack helicopter, the Huey Cobra, as an interim solution for the ongoing conflict in Vietnam. The Cobra was a modified version of the original Huey and was considerably less capable than the Cheyenne in many respects, most notably speed. But it was a simple, affordable, and reliable option that could pack quite a punch. In fact, as a result of the relative success of the Cobra in Vietnam, the Army apparently redefined its requirements for a new attack helicopter. High speed was no longer an issue, but survivability was. The new aircraft would only have to reach a top speed of roughly 185 miles per hour, but it would have to be equipped with 2 engines as opposed to the single engine that drove the Cheyenne. When Lockheed heard of the new requirements, it proposed a twin-engine propellerless version of the Cheyenne. But there were other problems that were hampering further continuation of the program. For one thing, Lockheed's projected cost for each aircraft had risen from $1.5 million in 1966 to well over $3 million in 1971. The Cheyenne already appeared doomed when a final incident took place that ultimately sealed its fate. During a crucial meeting with government officials to determine if the program would continue to receive funding, a pair of TOW missiles were fired to demonstrate the system's phenomenal accuracy. Dozens of TOW firings had been conducted without a single glitch. But this time would be different. The first missile fired drove straight into the desert, missing its target completely. After the demonstration, Lockheed officials desperately tried to explain that the TOW missile had a failure rate as high as 10% and that they had never had a failure before. But it would do little to remedy the situation. On August the 9th, 1972, the Cheyenne development contract was officially terminated. While the missile failure alone did not kill the project, it is clear to many who worked on the Cheyenne that it provided the final excuse for those who opposed its ultimate success.